So, welcome back student. In the last class we start a very important concept which is eigenvector and eigenvalues. So, we calculate some eigenvalues, but we did not calculate the eigenvectors. Also mentioned that eigenvalues may be distinct and it may be same. If it is distinct, then I have some extra property with that. So, we will explore these things in this class. So, let us start with one matrix, say A is 3 4 minus 1 minus 2. By the way, I should mention at this point one important thing, that the procedure that I am following is always for 2 by 2 matrix, but this procedure is exactly same for 3 by 3 and other dimension. This is not a very different thing that is done in 2 by 2. It is easier, it is showing, I can get the result quickly, that is why I am always using a 2 by 2 matrix. But when you practice, you should also practice for 3 by 3 matrix. It is important to calculate for 3 by 3 matrix how you calculate the eigenvalues or eigenvectors, but the procedure is exactly the same that I am doing here. Apart from that, I also like to mention before calculating the eigenvectors and eigenvalues for this matrix, I will also like to mention two important things. Say A is a matrix and I have the eigenvalue, say this is a n by n matrix and I have n lambda 1, lambda 2, lambda n number of eigenvalues. So, there is a relationship between, last class I mentioned there is a relationship between eigenvalues and these eigenvalues with this matrix trace and all these things. So, please note it, very important. I will check anyway, I will check for this and all other cases, that summation of lambda I stands for 1 to n is nothing but the trace of a matrix A. I believe many of you know that, but still it is my duty to show or the mention this property, this important property. So, once you calculate the lambdas and if you add them, it will be the same as the trace of this matrix. This is one property, and the second property is if you multiply lambda 1, lambda 2, lambda n, it will be equal to the date of this matrix. So, lambda 1, lambda 2, lambda 3 is the n matrix that you multiply, and when you multiply the n number of lambdas, whatever the lambda you are getting, that will be equal to the determinant of matrix. So, with these two information, very important and vital information, you can always cross check that whatever the lambda 1, lambda 2, lambda 3 is you are getting is the correct or not. I will going to do that for this matrix, you can do that for other matrices also. You should remember that. Okay. So, my secular equation for this matrix will be 3 minus lambda minus 1 4 minus 2 minus lambda is equal to 0. Determinant of this quantity is equal to 0. So, what I will have 3 minus lambda with a negative sign, 2 plus lambda and plus 4 is equal to 0. So, first I need to calculate these things, that what is the value of lambda by using this equation. So, let us do. So, here I have 6 and then 2 minus, and so 1 plus lambda seems, and then minus lambda square plus 4 is equal to 0. So, I have minus lambda square plus lambda and then here I have minus 2 is equal to 0, or lambda square minus lambda plus 2 is equal to 0. It seems me that I can factorize that. So lambda lambda square I need to have a minus, so plus, so okay, I am making one sign mistake, so let me check where I am doing that, is equal to 1. So let me find that where I am doing the mistake. So it is 3 minus lambda 2 plus lambda with a negative sign, fine, and then multiply. So this is a minus, so there should be a plus sign here, and if a plus sign is here, then minus 6 and then minus 2 lambda and plus 3 lambda, so 1 lambda is here, and minus lambda square plus 4. So this minus sign gives, okay, here I am doing one mistake. So this minus sign is plus, this is plus, and this will be minus, and this will be minus 6 and plus, so it will be minus 2. So it is something like that. Here I am making small mistakes. So now I think I should factorize that. So it will be lambda minus 2 lambda plus 1 is equal to 0. This I can factorize, and I am getting this value. So lambda square minus lambda 2. So what lambda value I am getting? Lambda 1 is 2 and lambda 2 eigenvalues I am getting, which is 1 and 2 and minus 1. This, the first part is done. So now I am going to cross check whether these values what I am getting is correct or not. So my lambda 1 plus lambda 2 should be trace of A. Here trace of A is 3 minus 2 1. So lambda 1 plus lambda 2 is 2 plus minus 1 is equal to 1, which is equal to the trace of the matrix. So first thing is correct. Second thing is the determinant of that. So what is the determinant of A? So the determinant of A is 3 into 2 is a minus 6 and then minus with a plus sign and then 4. So it will be minus 2. If I multiply lambda 1 and lambda 2, it will be also minus 2. So my trace and determinant which is related to lambda 1 and lambda 2 is also, I can verify that this is correct. Fine. So I can now calculate the eigenvector, because so far I did not calculate the eigenvector, I just mentioned about the eigenvalues. So eigenvalues, let me write it here somewhere. Lambda 1 is 2 and say lambda 2 is minus 1. This, now I am going to find out the eigenvalues. How the eigenvalue will be there? So if you remember, my equation was something like this, the eigenvalue equation. For 2 by 2 matrix, if I write, so my this is x1 x2 that I need to find out. A is this value, now for 2 lambda I should get 2 different eigenvectors. So lambda, say for 2 x1 x2, I should have two equations, and if these two equation I can, if I solve that, then I will get the value of x1 and x2, but always you will get a relation. Why you are getting a relation, I will explain. So, let me first find it. 3x1 minus first equation minus x2 is equal to 2x1. So, from here I can have this 2x1, if I put it here, then it will be x1 minus x2 is equal to 0. This is my one equation in a simplified form. What about the second equation? 4x1 minus 2x2 is equal to 2x2. If I put it here and take 4 common, I will get the same equation back, x1 minus x2, nothing new. Two equation I get, but the same two equations are same to each other. So, I am not getting any unique result for that. Why I am not getting unique result, I will explain. So, let me first find out how to do these things. Always you will get these things. So, what you will do, that you know x1 is equal to x2. Now, you need put your arbitrary value. So, x1 I put 1, then x2 has to be 1. So, my first eigenvector for lambda is equal to 2 is here. So, let me write it here. So, my first eigenvector for lambda equal to 2 is 1 1. I normalize that. So, I make a 1 over root over of 2, I make a normalize that. So, this is my first eigenvector. Now, why I am not getting these things? If you check that, you will find if this is a eigenvector x and x, then any multiplication, if I multiply any number with this side and this side, that will be automatically the eigenvector of A. So, there is an infinite number of possibility to have eigenvector. If I multiply any number with this 5, 6, 7, whatever the number you multiply, that will be automatically the eigenvector of this. So, that is why you are not getting any unique relationship between these two, but the important thing is that you are getting the relationship between two components, that is important, always you will do. And once you get the two components, you can get the relationship, and this from this relationship you can find out what is the eigenvectors. Okay. Now, I will do the same thing. I will do the same thing for another lambda, which is minus 1. The equation will be same, except lambda should be replaced by minus 1. So, okay, let me clearly write it. It will be minus 1. So, again I will have two equations for that. So, 3x1 minus x2 is equal to minus of x1, that is my first equation. From this equation I can, if I put it here, then I will have, from this I will have 4x1 and then minus of x2 is equal to 0. Again I have a relationship this. For the second equation, if I do, let us try to find out what is coming in the second equation. Is there anything new I can get from this second equation or not? Is minus of x2. Now, if I put this x2 here, 4x1 minus of x2, I will get the same. So, two same equation I always get, and now again if I put one value, then I need to find is what is the other value. So, if I put x1 say equal to 1, x2 will be equal to 4. So, what will be the eigen vector for that? So, for if I write for lambda is equal to say -1, I have x which is 1 4, and in order to normalize that, I always, as I mentioned, if I multiply any number, that will be automatically the eigenvector of that. So, I can normalize that. So, if I normalize, it will be root over of say 17, 1 square plus 4 square root over of that. So, it will be, so 2 eigenvectors I can generate from that for 2 eigenvalues, and these 2 vectors are like this. So, final thing is, for this I have lambda 1 is 2, lambda 2 is -1, and for that I have an eigenvector 1 root over of this 1 1, and for that I will have 1 normalized from this. Okay, fine. So, next I will want to find out another important thing, that one very important theorem. These eigenvectors, these eigenvalues are linear, these eigenvalues are distinct to each other, that means they are not same, they are not same. If they are not same, if they produce the eigenvectors, then these eigenvectors can be always linearly independent to each other. That is a very important thing. So, let me do this and write it clearly, but before that let me calculate another, for another matrix let me calculate say 1 -1 0 1. What will be the eigenvalue and eigenvector for that? So, the characteristics equation will be 1 minus lambda -1 0 1 minus lambda is equal to 0. It will be 1 minus lambda square is equal to 0. So, this is a matrix 2 by 2 matrix where the eigenvalues are same, 2 eigenvalues have the same value. So, these eigenvalues are not distinct. This is a different example where the eigenvalues are not same, that is done in the previous example where lambda 1 and lambda 2 are different, but here I have one matrix where eigenvalues are same. So, what is the difference between the same eigenvalue and different eigenvalue, that I want to find out. So, let us, so the theorem suggests that if lambda 1, lambda 2, lambda n are n distinct eigenvalues of a matrix A. So, lambda 1, lambda 2, lambda 3 are n distinct eigenvalues of a matrix A, then the corresponding eigenvectors will be linearly independent to each other. So, very important statement. The statement suggests that, for example, I have A and I have phi 1 a vector, I have lambda 1 phi 1, a phi 2, lambda 2 phi 2, and so on, a phi n, lambda n phi n. So, I have this amount of equation. Every cases I use the eigenvalue equation with different eigenvalues. For lambda 1 I have a eigenvector phi 1, for lambda 2 I have a eigenvector phi 2, and so on. For lambda n I have a eigenvector phi n, and if lambda 1 lambda 2 is not equal, so that means lambda 1 lambda 2 lambda 3 are distinct, they are not equal to each other. So, no lambda I is equal to any of lambda j, they are not equal, any of them are not equal to each other, all are distinct, then phi 1 phi 2 phi n, these eigenvectors are linearly independent. That is the meaning of these things. So, I will going to try to prove that, and then we will see this proof. This is a tricky proof, but it is an important conclusion that you should note, that if a eigenvectors, whatever I am whatever the value of eigenvalues are there, if they are distinct, then from that I can always generate the eigen vectors which are linearly independent to each other. So, let us try to prove that, which is a tricky one, but it is important, the conceptually this is important. So, let us start with this equation. So, phi 1 phi 2 phi n, as I show, are the eigenvectors, are the eigenvectors phi 1 phi n, these are the eigenvectors. So, I am demanding that these should be linearly independent. That means C 1 phi 1 plus C 2 phi 2 plus C n phi n is equal to 0. I can put this equation, if I put this equation, then if phi 1 phi 2 phi n are linearly independent, then the only trivial solution is C 1 is equal to C 2 is equal to C n is equal to 0. So, I need to prove that if these are the eigenvectors of A with distinct eigenvalues, then this is 0. How to do that? So, what I will do that, say this is equation 1, I will operate A minus lambda 1 I over this C 1 phi 1 plus C 2 phi 2 plus C n phi n is equal to 0. I will operate these over that. When I operate, so A, if I operate over that, then what is the value I will have? C 1, first I operate this over that. So, first thing I have is C 1 lambda 1 minus lambda 1 phi 1, because if I operate over that, see A phi 1 is lambda 1 phi 1 and lambda 1 phi 1 is lambda 1 phi 1 with I. So, I will have my first expression this for first value. What will be the second value? The second value will be C 2, I operate A over phi 2. So, I will have lambda 2 minus lambda 1 then phi 2. If I go on, then I will have my final term C n lambda n minus lambda 1 phi n is equal to 0. Now, the first term you can see that this is 0, lambda 1 minus lambda 2 is 0. So, what equation, after putting this operation over that, what equation I am getting? I am getting a new equation which is C lambda 2 minus lambda 1 phi 2 plus C n lambda n minus lambda 1 phi n is equal to 0. This equation is coming from this to this after having this operation. So, next thing what I will do, that I will operate. So, this is my equation 2, I will operate a minus lambda 2 I over that. So, a minus lambda 2 I operate over my new equation fine. So, if I operate, then what happened, what will be my first term? So, let me erase this, also erase this I do not require that. So, what will be my first term? My first term will be C 2 multiplied by lambda 2 minus lambda 1, then a will operate to over that and lambda 2. So, I will have lambda 2 minus lambda 2 phi 2, that I have. Then what will be my second term? These over C. So, C 3 lambda 3 minus lambda 1, then a over that. So, lambda 3 minus lambda 2 and then phi 3 and so on, and finally, I will have C n lambda 3 lambda n minus lambda 1 lambda n minus lambda 2 phi n is equal to 0. Now, I believe, now again this C 2 term will vanish because lambda 2 minus lambda 2 is here. So, if I go on with that, with n minus 1 operation, then finally what I am getting, if I go on with these things, and at n minus 1 operation, if I do that so n minus 1 time, then I will have one equation, final equation, because C 1 vanishing in the first operation, C 2 vanishing in the second operation, third operation you will find C 3 will going to vanish and so on. So, in the last operation you will have an expression like this. This is my operation, at n minus 1th operation I will have. Now, important thing is all the lambdas are distinct. So, here you will find lambda n minus lambda 1, lambda n minus lambda 2, lambda n minus lambda n minus 1. So, that means if I say that since it is a distinct, so it will not be 0, phi 1 is not be 0. So, what will be 0? C n will be 0, that is my first conclusion, Cn is equal to 0. If Cn is equal to 0, whatever the equation I have, start with the equation is something like this. I should stop here and say my new equation is this, because C1 I calculate this, C1 is 0. Now this is the one part. Next part is that I start with this equation and again operating with that a minus lambda 1 I operate over this and do that in n minus 2 time and then find Cn minus 1 is 0. If I do that, again I will have one equation and do the same thing, I find Cn minus 2 is equal to 0 and gradually I find C1 equal to 0. So all the Ci's you can say with this operation, if I do that this operation repeatedly, I can show that C1 is equal to C2 is equal to C3, Cn is equal to 0. So my starting equation was something Ci phi I is equal to 0. Now I am saying if it is 0, then this equation only satisfied for all Ci is equal to 0. That means phi I are linearly independent vectors. So whatever the phi I have is the linearly independent vectors. When I am getting these things, when all the lambdas are distinct to each other. So with this proof, it is a very important concept. We know that if a matrix have a eigenvalues which are distinct, which is not same to each other, then you can find a corresponding eigenvectors, they are linearly independent vectors. This is a very important concept and you should remember this concept, it will help you in future. So with that today I would like to conclude that. In the next class we will learn more interesting things related to matrix, which is diagonalization of this matrix. So with that let us conclude this. So in the next class we will start from this concept, we may use this concept little bit and then find how to diagonalize a matrix. So this is a very important thing also with that. So see you tomorrow in the next class.